Welcome to the lesson Crankcase Ventilation Issues in Hydrogen Internal Combustion Engines. In this lesson, we will discuss why crankcase ventilation is crucial for hydrogen internal combustion engines and how improper ventilation can lead to ignition hazards and oil contamination. Let us look at our lesson objectives. By the end of this lesson, you will be able to explain why crankcase ventilation is more critical in hydrogen engines as compared to gasoline engines. Next, you will be able to identify the safety hazards associated with hydrogen accumulation in the crankcase. Following that, you will be able to describe the function and importance of pressure relief valves in hydrogen engine crankcases. Then, you will be able to explain how inadequate ventilation leads to water contamination in crankcase oil. Finally, you will be able to recognize the consequences of improper crankcase ventilation on engine performance and longevity. Let's start by looking at the introduction to crankcase ventilation in hydrogen engines. Crankcase ventilation serves as a critical function in all internal combustion engines, but it becomes even more important when we're working with hydrogen fuel. The unique properties of hydrogen make proper ventilation not just a maintenance issue, but a safety requirement that must be carefully managed and controlled. The crankcase is the lower part of the engine that houses the crankshaft and contains the engine oil. In any engine, gases can leak past the piston rings into this space. With hydrogen engines, we must prevent these gases from building up because hydrogen behaves very differently from gasoline vapors. Technicians and engineers working with hydrogen engines must understand how ventilation systems function and why they're designed in a particular way. This knowledge helps prevent dangerous situations and ensures the engine operates safely and efficiently over its service life. What is crankcase ventilation? Crankcase ventilation is a system that continuously removes gases from the crankcase and either vents them to the atmosphere or routes them back into the engine's intake system to be burned. So, how does a crankcase ventilation system work? The system uses the pressure difference between the crankcase and either the atmosphere or the intake manifold to create airflow. Fresh air enters the crankcase through a breather, flows through the crankcase space, picks up any blow-by gases, unburnt fuel, exhaust gases, and vapors, and then exits through a ventilation valve or hose. Let's look at the basic components of the crankcase ventilation system. They are a positive crankcase ventilation valve, a breather or air inlet, ventilation hoses, and an oil separator. The positive crankcase ventilation valve regulates the flow rate of gases leaving the crankcase in response to engine vacuum. The breather or air inlet allows fresh air to enter the crankcase. The ventilation hoses connect the crankcase to the intake manifold or atmosphere. In some systems, the oil separator removes oil mist from the gases before they're vented. By maintaining this constant flow of air through the crankcase, the system prevents the accumulation of harmful gases, removes moisture, and maintains proper pressure inside the crankcase. In hydrogen engines, this flow must be sufficient to prevent hydrogen concentrations from reaching ignitable levels. We will now discuss hydrogen blow-by and ignition risk. During an engine operation, not all the fuel in the combustion chamber burns completely, and some of this unburnt fuel can slip past the piston rings. This process is known as blow-by, and it occurs in both gasoline and hydrogen engines. The piston rings create a seal between the piston and the cylinder wall, but this seal is not perfect, allowing small amounts of gas to escape into the crankcase below. The key difference with hydrogen is its ignition characteristics. Hydrogen requires much less energy to ignite compared to gasoline. Where gasoline vapors need a specific concentration and a relatively strong ignition source, hydrogen can ignite with very little energy and across a much wider range of concentrations in air. Because hydrogen ignites so easily, any hydrogen that enters the crankcase poses a real ignition risk. If the right conditions exist, a mixture of hydrogen and air, combined with any source of heat or spark, can ignite. This makes hydrogen blow-by more dangerous than gasoline blow-by. The solution is continuous ventilation. By constantly moving fresh air through the crankcase and expelling gases, we prevent hydrogen from reaching concentrations that could ignite. The ventilation system must be designed to handle the specific flow rates required to maintain safe hydrogen levels at all times. Now, let's look at the consequences of crankcase ignition. When hydrogen ignites inside the crankcase, combustion happens very rapidly. This rapid combustion creates a sudden increase in pressure within the enclosed crankcase space. The crankcase is not designed to contain high pressures, unlike the combustion chamber, so this pressure spike creates an immediate problem. The severity of crankcase ignition results varies. In the best case scenario, you might hear a loud bang or popping noise as pressure escapes through the seals or the ventilation system. This is startling but may not cause immediate damage. In the worst case, the pressure and heat can lead to seal failure, oil leaks, and even engine fires that can damage the entire engine or surrounding components. To protect against dangerous pressure buildup, hydrogen engines must have pressure relief valves installed on the valve cover. The valve cover is the top part of the engine that covers the valve train. This is an ideal location for a pressure relief valve because pressure rises upward and the valve cover provides easy access for installation and maintenance. The pressure relief valve acts as a safety device. When the pressure inside the crankcase exceeds a predetermined limit, the valve opens automatically, allowing the pressure to escape in a controlled manner. This prevents the pressure from building to levels that could blow out seals, crack the crankcase, or cause other catastrophic damage. The valve then closes automatically once pressure returns to normal. We will now look at water vapor contamination from exhaust gases. Blow-by doesn't consist only of unburnt fuel. Exhaust gases from combustion can also slip past the piston rings and enter the crankcase. This happens during the exhaust stroke when pressure in the combustion chamber pushes gases downward past the rings. When hydrogen burns, it combines with oxygen to produce water vapor. This is different from gasoline engines, where combustion produces carbon dioxide, water vapor, and various other compounds. In a hydrogen engine, the exhaust is primarily water vapor, which means the blow-by gases entering the crankcase contain significant amounts of water vapor. The crankcase is cooler than the combustion chamber, so when hot water vapor enters this cooler space, it condenses into liquid water. Without adequate ventilation to remove this water vapor before it condenses, water droplets accumulate in the crankcase over time. This liquid water doesn't stay separate from the engine oil, it mixes into it. You can see this as a milky appearance in the oil or as droplets on the dipstick. This water contamination is a serious problem that affects how well the oil can do its job. We will now look at the impact of water contamination on engine lubrication. Engine oil is carefully formulated to provide a protective film between metal surfaces that slide or rotate against each other. When water mixes with this oil, it disrupts the oil's molecular structure and reduces its ability to maintain this protective film. Water and oil don't naturally mix well, so the water breaks up the uniform oil coating that should exist on engine surfaces. When the oil loses its lubrication effectiveness, friction throughout the engine increases. The crankshaft bearings, piston rings, cylinder walls, camshaft, and valve train all depend on proper lubrication. Higher friction means these components rub against each other with less protection, generating more heat and resulting in greater physical contact between metal surfaces. The increased friction and reduced lubrication lead to accelerated wear. Metal surfaces begin to show scoring, pitting, and material loss. Bearings can fail, cylinder walls can develop grooves, and piston rings can wear prematurely. In severe cases, this can lead to complete component failure, requiring major engine repairs or replacement. The solution is always maintaining proper crankcase ventilation. When ventilation systems work correctly, they remove water vapor before it can condense and contaminate the oil. This keeps the oil clean and effective, protecting all engine components and extending engine life. Regular inspection of ventilation systems and oil condition is essential for hydrogen engines to prevent these problems before they cause damage. Let's look at the summary for our lesson. Crankcase ventilation issues in hydrogen internal combustion engines. Crankcase ventilation in hydrogen engines is primarily a safety issue. Because hydrogen requires so little energy to ignite and can ignite across a wide range of concentrations, any accumulation in the crankcase creates a hazard that must be prevented through continuous effective ventilation. Every hydrogen engine must be equipped with pressure relief valves as a safety backup. These valves provide a controlled means of releasing dangerous pressure if ignition occurs in the crankcase. They're not optional equipment, they're essential safety devices that protect both the engine and the people working around it. Beyond the ignition hazard, hydrogen engines face a unique challenge with water contamination. Since hydrogen combustion produces only water vapor, blow-by gases introduce moisture into the crankcase. This moisture condenses and degrades the oil's ability to protect engine components. A properly functioning ventilation system addresses both concerns simultaneously. It removes hydrogen before dangerous concentrations can build up, and it removes water vapor before it condenses into the oil. Understanding and maintaining these ventilation systems is crucial for anyone working with internal combustion engines that use hydrogen. Thank you.